Alright, what we will do next is to look at some simple physical examples of simple harmonic motion. The most standard one of course is to say that you have a mass attached to a spring of spring constant k. So here is your mass m and it is supposed to move on some frictionless surface. So here is m, the spring constant is k and you attach the spring to a wall here and the mass undergoes simple harmonic motion oscillating back and forth. And this is the very model of simple harmonic motion which we wrote the equation of motion down for. Okay. Of course one could ask what happens if I took this mass and suspended it in the gravitational field of the earth, for example. So I suspend the spring vertically instead of horizontally and then it of course bounces up and down. And the question is that also simple harmonic motion? The answer is yes, and actually the more formal way of seeing this is the following. If I have simple harmonic motion for which the total energy is 1/2 mx dot squared plus 1/2 kx squared, I don't like to write it, as you can see, in terms of k and m, because the defining property of the simple harmonic oscillator is actually the ratio of these masses, the frequency. So let us put that in, and henceforth let us write this as 1/2 m x dot squared plus 1/2 m omega squared x squared, because k over m is omega squared. That is a much better way of writing this, because it immediately brings out this quantity here, and then the ratio of the frequency square is of course the ratio of these coefficients, and m cancels out and you get omega squared. Now what happens in this case is that the potential looks like this, V of x, and the particle is oscillating for a given total energy. It oscillates between minus a and plus a. This is the amplitude. Okay. Now suppose I shifted the center of oscillation to some other point. So let us suppose that the potential was like this. Here is the x axis, here is the V of x axis, and it is the same potential, but it is about some other point x naught, not necessarily the origin. As long as this does not change or this does not change, the parameters do not change, this does not matter at all. It will now oscillate about the point x naught rather than the point x, but with the same angular frequency omega. Now what is the potential energy in this case going to be equal to? It is equal to 1/2 m omega squared x minus x naught whole squared. So it is a parabola centered at the point x naught. And again it does not matter, because all I have to do here is to let x prime be equal to x minus x naught, and since this is a constant, the total energy now becomes E is equal to 1/2 m x prime dot squared, because whether I differentiate x or x prime with respect to t does not matter, because it is just a constant shift, plus 1/2 m omega squared x prime squared. So that is the old oscillator once again, except that the center of oscillation has shifted. And this is what happens, for instance, if you put this oscillator in, you attached a spring and then the mass here m, and you also had gravity acting downwards. So there is an acceleration due to gravity acting downwards. What happens is that the equilibrium point is not at zero extension of the spring, but rather it extends a bit under gravity, and that is the equilibrium point. And then if you pull it a little bit and let go, it oscillates up and down about that new point, but the frequency does not change, it is exactly the same. Of course if you change the potential by adding some other force to it, something that makes it depart from the x squared form, if there are other terms here like x cubed and so on, then you are in trouble always. What I did by putting it under gravity was to change this by adding an x term, mgx, and then I can bring it to this form by completing squares. So if the new potential energy is this plus mgx, you can see that I can complete squares and make this x minus x naught squared plus some constant. And all that the constant will do is to shift the zero level of the energy, but the physical oscillation will still happen about the new center of oscillation, and that will be determined entirely by this coefficient. So I urge you to try this out as an exercise by adding a force of gravity here, force due to gravity, a potential here, and then asking what happens in this problem, what happens to the frequency of the simple harmonic oscillator, and in this case. But the trick is very simple, all you have to do is to square it and so on. But if you make it a more serious change, if you put x cubed, x4 and other terms here, so that the force is conservative but is no longer a simple harmonic force, no longer proportional to the displacement but to some higher power of x, then it is no longer simple harmonic motion at all. It may still be periodic motion, but it will not be simple harmonic motion at all. So the mass and spring was the simplest case. Well, let us look at a slightly more complicated situation, and this is the simple pendulum. So the simple pendulum in this case, the restoring force is actually provided by gravity, and what happens is that you have a point of suspension and you suspend a light massless rod with a heavy bob here of mass m, and this undergoes oscillations, angular displacement up to some point, and the instantaneous angular displacement is some theta, say, and it goes up to this point and back in this fashion. Then the question is this simple harmonic motion or not? Now what we have to do here is to write down a model for an expression for the potential energy. So in this case the total energy E is 1/2 ml squared, because this is L, and the energy is in rotational kinetic energy, as this this bob undergoes an angular displacement, and that rotational kinetic energy is moment of inertia about this point of suspension O, which is ml squared, multiplied by the square of the angular frequency, which is equal to angular speed, which is theta dot squared. That is the kinetic energy here, plus the potential energy, and the potential energy comes because when it is displaced away from its bottommost point, where we take the potential energy to be 0 here, because the reference level is taken with respect to this equilibrium point, then the amount you have raised it by is this much, this difference here, and this difference is L minus L cos theta, and therefore this is mg L times 1 minus cos theta. So that is the total energy, and it does not look anything like theta dot squared plus theta squared. That would be simple harmonic motion, but this is not simple harmonic motion. Okay. But we can see physically what sort of motion it is by this procedure of plotting the potential energy, which is what you should always do. So this is the potential energy, and we should plot, here is theta and here is v of theta, which is mgl into 1 minus cos theta, and we should plot this function as a function of theta. And it is clear that when theta is 0, the potential is 0, and its maximum when theta is pi, then it is twice mgl, and then it periodically oscillates back and forth in this fashion. Okay. And this point here is pi, this is 2 pi, this is 0, this is minus pi, this is minus 2 pi, and so on. So for small oscillations of this pendulum about theta equal to 0, you have something like oscillation in this potential here. Now of course you could have a larger oscillation, you could go all the way up to pi on this side, up to minus pi on this side. If you go beyond that, it escapes this well and falls into rotation if you increase the energy sufficiently. But as long as the energy is below this value is 2 mgl when theta is pi, cos theta is minus 1, that is the largest value for which you can have oscillatory motion, then you are in a potential which looks like this, but this potential is not a parabola, it is 1 minus cos theta, right, and therefore the motion in general is not simple harmonic. but it is clear it is periodic once again, because what else will it do? If this were the total energy, the pendulum would oscillate between this angle and this angle, that is clear. But it is not simple harmonic. When does it become simple harmonic? It becomes simple harmonic when you can take this expression for cos theta and approximate it by the leading term in its power series for cos theta. So we have cos theta in radian measure equal to 1 minus theta squared over 2 factorial plus theta over 4 factorial minus dot 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 ad infinitum, and this is approximately equal to 1 minus theta squared over 2 for sufficiently small theta, close enough to 0. For sufficiently small theta. How small? Well, when you can neglect theta to the 4 compared to theta squared. So you specify a degree of accuracy and I tell you how big theta should be in order for the approximation to be good. Okay. Then in that case, for small oscillations, small amplitude oscillations, this thing becomes equal to 1/2 ml squared theta dot squared plus mgl over 2 theta squared. The 1 cancels out and then you have theta squared over 2 and that is it here. And this is now in the form of simple harmonic motion. This will immediately imply simple harmonic motion, because now you have a dynamical variable theta, the angular displacement, which has got a kinetic energy proportional to theta dot squared times the positive coefficient, a potential energy proportional to theta squared, positive coefficient. The ratio of these two will give you the angular frequency, and 2 pi over that angular frequency is the time period immediately. So this immediately tells you, this will immediately tell you that omega equal to square root of mgl over ml squared equal to square root of g over L. So the time period is 2 pi square root of L over g for small oscillations. We do not have to solve the equation of motion for this, because from what we have seen, it is only the ratio of these two coefficients that determines the angular frequency and therefore the time period immediately. You could ask, all right, given this, I know that this will imply the equation of motion theta double dot equal to minus omega squared x, which is minus g over L theta in this problem. That is how you get simple harmonic motion, because we saw already that an equation of this kind, the total energy of this kind implies an equation of motion of this kind, and vice versa here. But now you could ask, all right, if this is so, what does this exact equation imply? What kind of thing will it imply? That is not hard to find either, because this thing here will imply that ml squared theta double dot, this quantity here, is equal to minus dv over d theta, because that is the potential, and the force on the right hand side is this thing here, and dv over d theta, as you can see, is mgl. You differentiate a minus cos theta, you got a plus sin theta, then you put a minus sign, so this is equal to minus mgl sin theta, or theta double dot equal to g over L sin theta. That is the exact equation of motion for a simple pendulum, and a simple pendulum becomes simple harmonic for small oscillations, and then this is the approximate equation of motion. And when is this valid? When theta is so small that the next term here in the expansion of sin theta can be neglected compared to theta. The next term is theta cubed over 6. So when you can neglect the higher corrections in the power series expansion of sin theta in powers of theta, then you get simple harmonic motion, and the time period is 2 pi root L over g. Okay. So here is a problem which is actually very nonlinear, very difficult, because in principle the equation of motion is quite hard to solve. It cannot be solved by elementary means because it is not an equation that is linear in theta. It is not the simple harmonic oscillator equation. It involves a sine theta here, which in principle has all powers of theta, all odd powers of theta. Okay. And yet in the small oscillation limit, the problem becomes very straightforward. It is not hard to see that the approximation we have made is equivalent to saying that sine theta is approximately theta, which is equivalent to saying that the motion is approximately in a straight line. It is essentially that approximation that has gone in here. So that is our second physical example of simple harmonic motion in the case of a simple pendulum, where small oscillations become simple harmonic. For the spring, that was the exact equation of motion, but for the pendulum that is not true. As soon as the amplitude exceeds a value such that you can't make this approximation, the time period depends on the amplitude. It is no longer simple harmonic motion. Well, let us look at an example which is taken from, say, fluid dynamics. And here is another example, which is oscillation of a fluid column. Let us suppose we have a U tube of constant cross section, although that is not essential for what I am about to say, and you fill it with water up to a certain level, and of course the levels are the same on both sides in this fashion here. And let us suppose that the cross sectional area of this tube, cross section, equal to A, for instance, okay, and the fluid density is some rho. Then when I pour this fluid in, you can see that if I push this a little bit harder here, the fluid goes up there, and then whatever is the excess height there comes down, and then the whole thing oscillates. And if there is no friction, this will go on forever. If there is friction, and we will talk about damped simple harmonic motion a little later, then of course the oscillations subside, but otherwise the fluid will oscillate forever. And the question asked is, now if I displace this a little bit so that I have a little excess x on that side, a height x, and on this side it goes down by the same amount, so this is also x on this side, then the question is, what is the time period of oscillation of this fluid column? Okay. Now that is easily found, because what is the force? The force appears because this level is out here and the other column has a level which is higher, and the difference in levels now is 2x. So you have something which is 2x times the cross sectional area times the density multiplied by gravity, and that is pushing down to equalize this. So minus this is equal to the acceleration of whatever is being accelerated, and that is the full fluid, the entire fluid. And let us suppose the entire fluid, when it is in equilibrium, this whole thing has a length L, say. Then the total amount of fluid is the mass, which is equal to rho times the cross sectional area, which I call A, so A here, times A times the length times x double dot. So it says mass times the acceleration x double dot of this little element is equal to the restoring force out there. Okay. So rho and A cancel out, and I have an equation which says x double dot equal to minus twice g over L x. This will imply that the angular frequency is equal to square root of 2g over L, or the time period equal to 2 pi square root of L over 2g. So we can compute the time period of oscillation of this fluid element, assuming there is no damping. If there is viscosity, if there is stickiness and damping, of course it will damp out. That will come when we discuss the rate at which it damps will depend on the friction, and this we will discuss subsequently when we talk about damped simple harmonic motion. But you see, in this case I did not write the total energy down. I found it easier to write down the actual equation of motion, paying attention to the fact that what is offering inertia is the full fluid here, and what is producing the excess force is the difference in levels, the fluid column which corresponds to the difference in levels, and that gave us this expression for the time period of oscillation. Okay. Let us look at an electrical problem, an analogy. You are familiar with an inductor. In an inductance L, if you connect it to a capacitance C and an inductance L and you charge the capacitor, then what happens is the charge gets discharged through the inductor, and as the current voltage flows through, as the current flows through this L, there is a back EMF set up, and the charge will go from one plate of the capacitor to the other and oscillate back and forth if there is no resistance in the circuit. A little later we will put in a resistance and see what happens and how it damps out, but in the absence of the resistance, what you have to do is to ask what is the voltage that you have. The back voltage here is proportional to L times d. The charge on the capacitor instantaneously is Q, which is a function of t. Then this is L times dq over dt. Well, I should really write L times d2q over dt2, because it is the rate of change of the current or the flux that we are talking about. This plus q over c, that is the voltage across the capacitor, that is equal to 0 when you have free oscillations without connecting it to an external source. If you connected it to an external source of voltage, on the right hand side you would have a forced oscillator. It would have the voltage applied EMF. Okay. So here we are, this is the equation of the charge, instantaneous charge on the capacitor. Okay. But it is exactly the simple harmonic oscillator form, because this says q double dot equal to minus omega squared q, where omega equal to square root of 1 over LC. So the time period of oscillation t equal to 2 pi root LC in this problem. So we do not care, as you can see, whether it is angular displacement or a linear displacement or a charge on a capacitor or the height, excess height of a fluid column, we do not care. The phenomenon is exactly the same. Once you bring the energy down to that quadratic form, or you bring it the equation of motion to this form, you can identify what the angular frequency is and the matter is over. Okay. Now we have already seen that you could displace this oscillator by a certain amount and identify the frequency here, but you can do this in even more complicated situations. When you do not have simple harmonic motion, you can find out under what conditions there is simple harmonic motion. So let us look at another example where we have a particle moving in a potential, but the potential is complicated. I mentioned that if you took intermolecular forces, this central potential, in this case the V of r, which is an interatomic or intermolecular potential, in suitable cases has the following shape. As a function of the radial distance from one atom taken to be at the origin of coordinates, this potential has a shape which looks like this form. And I wrote down a form for this, which was V of r was equal to some constant V naught times a length scale A over r to the power 12 minus A over r to the power 6, to show that you have a very repulsive force for small values r less than A, some constant times A, and then you have attractive force beyond a certain point. So till this point dV over dr is negative, so minus dV over dr is positive, and therefore the force pushes you outwards radially. It is a repulsive force, and beyond this point, wherever this point is a minimum, the slope is positive, so minus the slope is negative and the force is radially inwards. So you have repulsion and attraction. So this potential models the fact that when you bring two atoms very close to each other, electrically neutral atoms, there is a repulsive force, but when they are sufficiently far apart, there is a weak attractive force, okay, in this form. Now if you put the second atom in this potential well, it will undergo oscillations about that point. Now this is not a parabola, so the motion is not simple harmonic in general, okay. But if you call this point wherever the minimum is, which is 2 to the 1/6 times a, as you can find out from there, so let us call this point r naught, then as long as you have very small amplitude oscillations about this minimum, and it is a simple minimum always looks like a parabola in between. So as long as you have small oscillations about this point, the potential V of r about this point can be written as V of r naught plus, and I do a Taylor expansion of this potential about that minimum. And the Taylor expansion, if you recall, says the value of the function at point r is a value at some given value point r naught plus r minus r naught times the first derivative at that point plus square times the second derivative and so on. So the first term is r minus r naught V prime at r naught plus r minus r naught squared over 2 factorial V double prime of r naught plus dot dot dot, where a prime denotes the derivative with respect to r, and then you put r equal to r naught after you differentiate. But this is a point of minimum for V of r, and therefore at a minimum the slope vanishes. This term is therefore 0 by definition, because V prime of r naught is identically 0 at that point. Then the potential looks like a constant. This fellow is a constant. We do not care what it is. It does not play any role at all. We have seen that in a simple harmonic oscillator problem, if you add a constant to the total energy, nothing happens. The frequency does not change at all. So we have a system where we can write a kinetic energy plus a potential energy which looks like this quantity. But this is a constant. This quantity is a constant, and therefore the motion is simple harmonic, provided this quantity must be positive. The effective spring constant must be positive. Only then do you have simple harmonic motion. Is it positive? Well, the answer is yes, because at a minimum the second derivative is positive. Had this been a maximum of the potential, that would have been negative, but because it is a minimum, we are guaranteed that this is positive. Now I ask, what is the frequency of oscillation of this second molecule about this equilibrium point? And the answer is very simple. All you have to do is to put in the mass of that particle, and essentially V double prime of r0 over 2 factorial over 2 is the square of the frequency apart from that factor of this mass, because the ratio of coefficients determines what the frequency is. So in this problem, hard as it looks, it is very easy to find what will be the basic frequency of oscillation or vibration of one atom due to the potential of another, and so on. So it is like a shifted oscillator about this point. Of course, you go to higher amplitudes, it is no longer simple harmonic, and you have many more complicated phenomena happening here. But in this lowest level approximation, it is an oscillator. Now I leave an exercise as an exercise, the following problem. Take two charges on the x-axis, put a charge q, a positive charge q at the origin, and fix a charge capital Q at the point A on the x-axis, that is at the origin, and another charge capital Q at the point minus A. These two charges are fixed, and this charge is free to move, and now imagine that you displace it slightly about through an amount x on the positive side and let go, then this charge is going to oscillate, because the force due to repulsive force due to this is greater than the attractive force due to this, repulsive force due to this. As it moves here, the repulsive force pushes it back. Similarly, when it comes here, the repulsive force due to this, pushing it to the right, is greater than the force due to this, pushing it to the left, and therefore it will oscillate. Now what you need to do is to find the frequency of these oscillations. and hence the time period. What you need to show is that the restoring force is proportional to x for small values of x compared to a, small displacements compared to a, and that should help you to read out by writing the equation for the force for small x. You should be able to read out what the time period is from the frequency, angular frequency. So I leave that as an exercise.